Okay, hi everyone. Can you wave your hand if you can hear me okay? That's what I like to see. I have you here under false pretenses. We're going to talk about electromagnetic compatibility, and I'm going to try and teach you almost everything I know in about 30 minutes. This is 15 years worth of experience going into 30 minutes. Things may fall out, things may not be covered to your preferred extent. If there are any questions, you can come and see me afterwards at our stand. My name is James Pawson. I work for Unit 3 Compliance. We're a test laboratory based up in Bradford, West Yorkshire. It's the land of whippets, flat hats, and proper cups of tea. We also do EMC training, product design for EMC training as well. That's held up in Leeds, but we occasionally do it for other companies around the country. I like electromagnetic compatibility. It is by far and away the single best job I've ever had in electronics. It encompasses so much physics, legal, regulatory, product design, compromises, thermal, you name it. EMC has an effect on it, and it will have an effect on EMC as well. It's a measure of how compatible are products that we make, how compatible are they with the electromagnetic environment that they're operating in. Electromagnetic environments vary greatly between the environment that we're in now, maybe with a few radio transmitters, to, let's say, in a car or on an aircraft carrier. They're very different. EMC does not stand for easy money consulting. It is the hardest job I've ever had. It also does not stand for end of my career. I'm still working in this field. We make things. We make things that do things with electronics in, hopefully. If you make things that don't have electronics in, may I suggest you're probably in the wrong talk. When we make things with electronics in, they have the ability to emit interference, emit noise in the radio frequency spectrum, be it radiated or conducted on cables. And they also have the ability to receive noise in the electromagnetic spectrum. How does our product react when it receives noise? This is the study of the field of electromagnetic compatibility. From the emissions perspective, the problem is this. This is the radio spectrum for the United States of America. What do we notice? It's very full. Everything is spoken for. Once, twice, 10 times over in some cases. You've got 10 different radio systems all trying to use the same piece of spectrum. So whatever frequency we're emitting noise at, we're treading on someone's toes. We have the potential to cause interference to other licensed spectrum users. Licensed spectrum users like emergency services, amateur radio, air traffic control, space communications, military. Some of these people are going to be very, very annoyed if you tread on their toes. They're going to be so annoyed that they will actively prosecute anyone who's found to be trespassing on their bandwidth. Mobile phone operators are famous for this. Mobile phone operators, Vodafone, O2, Orange, or EE as they are now, I don't keep up to date, they actively prosecute, they actively track down any infringement with their radio bandwidth. So if you are going to cause an interference problem, just avoid the 1.7 to 1.9 gigahertz spectrum. That's my top tip for the day. But their enforcement powers go all the way up to legal enforcement. They can legally compel you to remove your products from service to perform mitigating actions. From the immunity perspective, we have to consider where our products are being used, in what electromagnetic environments those are being used in. So we have the concept of a controlled electromagnetic environment, a shielded room. No noise gets in, no noise gets out. This is like the EMC chamber that we take our products to be tested. A field in North Yorkshire is pretty quiet from an electromagnetic perspective, unless sheep are radio controlled these days, which I don't think they are. Contrast that with the flight deck of an aircraft carrier. We've got incredibly high-powered radar systems, electronic warfare systems. It's a very hostile environment for our electronics to work in. So we have to know what environment we're designing our product to go into. The problem with immunity is when our product is on our bench in a laboratory and everything's working fine, we're very happy with that. As soon as we introduce noise, what happens? If we've not designed our product correctly, performance will change. We're looking for the performance to stay within the manufacturer's guidelines, our specification for what the product does. There can also be a functional safety aspect to EMC as well. I'm imagining I'm driving in my self-driving car. I don't have a self-driving car. I would like one. It would make the journey to work a lot easier. I'm driving my self-driving car down the motorway and my phone goes off. All of a sudden, the self-driving car detects that there's a truck in front of me and puts on the brakes. There was no truck. It's electromagnetic interference from my phone into the car systems. That could cause a massive accident on the motorway. Medical devices. We don't want to be in intensive care on life support systems and for the security guard to come into the operating suite, look around, key his radio and say, yeah, it's all right, mate, it's all quiet in here. And my life support system turn off. So whenever there's a functional safety aspect to EMC, our immunity levels, the noise that we would inject into our systems, have to be proportionally much higher. Really, the main problem with poor immunity performance is it's not the regulators that are going to come to you and say, hey, your product is interfering with this or your product is low quality. Your customers are going to let you know. Your customers are going to be the ones that give you the 1-star review. Oh, I tried to connect it, but the USB kept disconnecting every time, or it just picks up random interference. It's a rubbish product. It's a low quality product. That's the perception. This can also be perceived as no fault found field returns. We put something out into the field, the customer has problems with it, we get called out, we get it back, we put it in the lab, we don't see any problems. We don't see any problems because we've removed it from the noise source that was in the field. So characterizing our products before we sell them as to their performance with electromagnetic noise is very, very important. So EMC, it's an environmental test specification. It's an environmental test specification just as we design something to have adequate thermal performance, adequate mechanical rigidity for the environment that it goes into, adequate electrical safety. It's an environmental test specification, and we have to treat it as such. We put it into our specification, we design to it, and we make sure we test and verify so that it is compliant, it is going to pass, it is going to operate correctly in those environments. It's easier said than done. EMC regulations are very concerned with inter-system interference. The interference between this laptop and the microphone, the interference between a mobile phone and a car. So we're interested in our system and how it reacts with other systems, either receiving noise or transmitting noise. There's also the concept of intra-system interference, interference within the same system that we've designed. And now it's not an external system that we're worried about. Now we're worried about things, internal components interfering with other internal components. For instance, a common case is poor quality HDMI leads causing in-band interference with Wi-Fi, all on the same board. You know, this could pass the EMC emissions tests, but it will not give us a good quality product. We have a swear jar. We have a swear jar at work. And if anybody says to us, oh, but EMC, it's all black magic, they have to put £1 in the swear jar. EMC is not black magic. Sometimes it can be quite complex, it can be quite hard to understand because we're dealing with elements that we didn't explicitly design. We're dealing with parasitic elements that exist within our design that we now have to try and deal with. There's also nothing magical about the colour green and yellow. If we see green and yellow, that's there for an electrical safety reason. It's not there for an EMC reason. It can have an effect, sometimes good, quite often not. Really, EMC is a test of what works on our bench. Does it work in real life? So we can design something on our bench in a relatively controlled environment, but does it survive in the real world? And it's also a really interesting game. We're playing a game because we all work for companies. Companies exist to make money. We exist to make products and we exist to make money. There's a compromise, there's a balance. On one hand, we have engineering, we have legal, we have all of the things that make us do more compliance, and that tips the seesaw this way. We spend more time, more money, and more effort to make sure that our designs are compliant, that our designs are good quality, that they can survive in this electromagnetic environment. However, on the other hand, we have the bad guys. Boo! Okay, fine. We have the bad guys, we have the commercial team, we have sales, marketing. They're saying, oh no, we can't spend that much money. Oh no, we have to sell it for this much, or we have to have it out yesterday. So that balance, the angle of our scale, that's our tolerance for risk. That's how much risk we can have. Do we want to spend too much money on compliance and potentially have a product that we now can't sell for the profit margins we need? Or do we save all the money and end up with a poor quality product? And you have to decide, you personally have to decide where you sit. Everyone has a different approach. If I'm Fred's Sheds and I'm making a shed monitor and I'm going to sell 3 to my friends Steve, Jerry, and Paul down the road, I'm going to have mostly a commercial focus. If I'm someone like Tesla or Ford who are making, critical circuits for their cars, I'm going to have a safety focus. There's always a balance. Okay, let's look at some of the physics, because the physics for EMC is absolutely fascinating. I promise no equations. Well, not too many. For radiated emissions, where do radiated emissions come from? Quick hands up. Who's had a radiated emissions problem with EMC? Okay, a good number of hands. Keep your hand up if it caused you significant cost and time delay on your project. You'll notice my hand is still up. £20,000 and 6 weeks in my case. I was not the program manager's favourite person. Where do emissions come from? Fundamentally, high-frequency currents. High-frequency currents on a wire, they generate high-frequency magnetic and electric fields. And due to the beauty of Maxwell's equations, the further we get away from our wire that's carrying this high-frequency current, the further we get away, the electric and magnetic fields start to combine. They start to combine, and if we're far enough away, we get a propagating transverse electromagnetic wave, a TEM wave. This is our classic radio wave that our mobile phones use, that broadcast TV uses. But we have to be far enough away at different frequencies. At some point, this transverse electromagnetic wave is going to hit a receiving antenna. And when it hits that receiving antenna, what happens? We've got the chance for noise to turn into interference. So by designing our product correctly, we can reduce the amount of radio energy that we emit. This is fairly simple. This is textbook stuff. The problem is that the products that we make contain magnetic field loops that have high currents, high frequency currents, and they have voltage sources that have high voltage changes. So we would say this is a high di by dt loop, a high dv by dt node, fast changing current, fast changing voltage. They're all in different orientations, different phases, different frequencies, different polarities. How they combine depends on what angle we look at the product. They might combine constructively or destructively. We might have phase addition or phase subtraction or any combination therein. This leads to quite a complicated radiated emissions pattern, which is why when we take our product and put it in the chamber, we do a 360-degree scan and we check our antenna, our receive antenna in the horizontal and vertical polarization. We're trying to map the electromagnetic response from our antenna. We typically do this inside an anechoic chamber. This is our anechoic chamber at our test lab. That's a very young me. This is quite a few years ago, before I had grey hair. We're putting out the equipment on the turntable. We've got our antenna. We rotate it around, and hopefully we see something like this. This is a good scan result. It's not failing. We also need to think about frequencies and wavelengths as far as radiated emissions goes. We need to consider what the wavelength of our signal is. We need to think about what the wavelength of our signal is so that we can avoid designing accidental resonant antennas. This is very easy to do. However, unlike that famous saying that oscillators don't, amplifiers do, it's very similar with antennas. You try and design an antenna to emit in a certain band, it's quite hard work. It's very easy to design a broadband, very effective antenna that gives us a lot of EMC problems. We always think about the classical resonant dipole, 2 elements a quarter of a wavelength long, 1 element half a wavelength long. So we might think that 100 megahertz, we need something that's 1.5 meters long. Actually, short antennas exist, and short antennas are very good radiators as well. Not as efficient as a dipole, but more than enough to cause us EMC problems. So it helps to have a mental model of what an antenna is. I like to think of an antenna as 2 conductors, 2 pieces of metal. They're conductors with a finite size, so they can have a magnetic field around them, therefore inductance. Separated by an impedance, so they can't be at the same voltage. And there's a capacitance. We've got 2 pieces of metal that can establish an electric field between them. They can see each other. We have a resonant circuit. L's and C's, it's a series LC resonant circuit. This is going to give us gain when we drive it at a resonant frequency. So we need to know where our antennas are in our products. We think of a typical dipole antenna. You've got long, skinny elements, and they come together. So you've got one element like this, one element like this. That's our antenna. What happens if we change the shape of those antennas? If we increase the surface area of those antennas, we establish multiple current paths on those antennas, we change the frequency response. So we go from having a narrow band antenna, shown here in green, with a very narrow band response, to having a broadband response, shown here in red. The peak gain is lower, but if we've got frequencies here or here, they're actually going to have more, there's going to be more radiation from that antenna. And we excite our antenna with high frequency currents. Or I should really say high fast changing currents, not necessarily high frequency. This animation from Wikipedia, this shows a 1 Hertz square wave, 1 Hertz. No one's ever had EMC problems from a 1 Hertz square wave, right? Well, potentially we can. What you notice is, as the faster the waveform changes from one state to the other, the more harmonics we have to add to get it to change quickly from one state to the other. So frequency is not necessarily the enemy, rise and fall time is. It could be rise and fall times from an LCD display, an LCD panel that we took apart because it had some problems. Here we've got a 60 megahertz clock going to a QSPI flash, and a very conveniently placed trace right next to it. All that energy couples onto there, couples onto the cable, radiates from the cable. It could be a very poorly designed DC to DC converter. Again, another one of the things that we've recently fixed. All of these noise sources are going to put noise harmonics, our switching frequency, and integer multiple harmonics all the way through our spectrum. If any of these coincide with a point where we have antenna gain, we're going to have a radiated emissions problem. Side note, it's also interesting, we need to check our equipment in different operating modes. We always think the highest frequency is the worst. Well, the highest frequency, in this case, isn't the worst. Maybe a slightly lower operating frequency is the worst. I'm now moving my third harmonic in line with a point where I've got more antenna gain. And that was the £20,000 6 weeks mistake that I mentioned earlier. We won't talk of it again. So now we have an interesting compromise. We have frequency versus quantity. As we get higher and higher in frequency, we get more and more resonant antennas in our product, because our products are of a finite size. As frequency goes up, our efficient antennas come down. We'll have more efficient antennas at 1 gigahertz than we'll have at 100 hertz. So the risk of radiation goes up with frequency, but the amount of energy in our signals comes down with frequency. So here we've got a lot of energy but no antennas to radiate it. Here we've got a lot of antennas but no energy to excite them. So in the middle we have this danger zone, usually in the sort of the 100 to 500 megahertz band. For typical digital electronics, this is where we see the majority of our radiated emissions. Conducted emissions, we're worried about long cables acting as efficient antenna. We're worried about coupling between circuits, either inductive coupling, capacitive coupling, common impedance coupling. Typically it's some kind of power supply, switch mode power supply, flybacks, forwards, boost, buck converters. We're worried about noise from our noisy switching node coupling into measurement circuits, LISNs, that we use to characterize how much current is flowing on our cables. The bright-eyed amongst you will spot that this is actually a low-frequency radiated emissions test. It's just easier to do it with a discrete adapter than it is with a really, really, really big antenna. Radiated immunity. How does it react to radiated noise through the environment? We're still designing the same antennas. We're designing the same antennas that are as good at receiving as they are at transmitting. If our parasitic antenna has a gain of 5 dBIs at 100 megahertz, that works in the transmit, it works in the receive. So this will easily put noise into our system. Our transverse electromagnetic wave interacting with a conductor causes currents to flow on the conductor. This is the reverse of radiated emissions. If we design a system that's good for radiated emissions performance, we improve its radiated immunity characteristics. But we also have to consider what's the circuit that's being excited by this noise. In the case of a simple op-amp with no filtering, whenever we hit that with electromagnetic noise, it's going to fail. The performance will deviate on the output. So now, for radiated immunity, it's not the amount of energy in the signal, it's the sensitivity of our circuits to this noise that we're transmitting. And again, we typically see radiated immunity problems most prominently in the 80 to 350 megahertz band. There's nothing special about 80 megahertz. Below this point, we start working on conducted immunity instead. It's easier to couple the energy into the cable directly. So conductor immunity, we're worried about noise sources like variable frequency drives, big broadband noise source, very, very significant problem in that kind of system. We're worried about arc and spark noise from relays, contactors, electromechanical switches, contact bounce drawing an arc. That arc will couple capacitively onto other cables, it will spread, it will cause interference with digital circuits. We're also worried about surges, lightning surges mostly, power surges. Lightning has kiloamps, kilovolts, very easy to couple large amounts of electric and magnetic fields into overhead power lines, and that ends up in our house and gives us some problems. Some EMC tests, like ESD, actually present both a radiated and a conducted component, and depending on the frequency, depending on which part of the curve, depending on which part of the discharge model we're dealing with, that can be a surprisingly difficult thing to deal with. It's been all doom and gloom. There are solutions. There are solutions to EMC. The first one is we don't test EMC in, like we don't test anything in, unless we've explicitly designed our equipment to pass EMC tests, it may not pass. We can't pretend to be surprised when it doesn't pass. Everything that we do is set at the design and specification stage. If this is mostly an audience of engineers, you already know this. Sometimes it can be a little bit hard to know how to design things in. The key tool in knowing about EMC is understanding where high frequency currents flow. I can see a few nods in the audience. You guys, you get it. As we go up in frequency, return currents in the ground plane of our circuit board, they start to follow the signal trace on the top layer. High frequency currents want to flow in the path of least impedance. Impedance defined primarily by the size of the loop and the inductance of that loop that it creates. As EMC engineers, it's our job to make, as design engineers, we need to control our loops very tightly and not let the magnetic field caused by those currents to leak out and cause emissions. We need to understand where fields exist between conductors. Two conductors carrying a high frequency current, the majority of the electric field and the currents are concentrated on the inside of that gap. It's trying to flow in the path of least impedance. Fields carry the energy. Current on wire is just a symptom of a nearby field that's carrying the energy. Currents themselves do not carry much in the way of energy at high frequency. There are some fantastic YouTube videos on that. Understanding all of how high frequency current flows allows us to design our systems. We can partition our systems, we can separate out parts of our system, so we can have noisy components like power supplies, mains input, and we can separate them from sensitive circuits like temperature sensors. This is a design review of a customer's product that we did recently, and they relayed out their entire system because they said, well, can we do some testing? I said, well, no, because it's going to fail. You know, we're going to need to rework the design before we do any testing. Oops. We need to understand there's nothing magical about ground. Anything on this image could be described as ground, whether it's the bond into the earth at the substation, separate issue, fascinating subject. The ground on our circuit board, DC negative, where is ground on here? Ground is not some magical hole that we can sweep all of our electrons into and they go away and stop causing us problems. It's just another conductor. It's a return conductor. We need to treat it with respect. When we have noise that will couple onto another circuit and cause interference, we can add filtering. We can deliberately design filtering to reduce the amount of noise radiated from our circuit. We're reducing the amount of noise that goes to the structure that's going to couple, and we can also add filtering on our inputs that reduces the amount of noise coming into our circuit and turning into interference. So we need to understand coupling mechanisms as well. We need to understand how inductive coupling, shared current loops, capacitive coupling, two pieces of metal that can see each other and force a displacement current through a capacitance, and the lesser spoken of common impedance coupling, where we have multiple circuits all sharing a same ground wire. Any voltage drop across there appears in series with all of the other circuits. All of these convey electromagnetic energy from one circuit to another circuit. We need to understand shielding. How does shielding work? How do we make a good shield? And also, how do we break a good shield? I've worked on products that have had full metal enclosures with massive holes drilled in them and cables passing straight through. You know, the shield's there, but they're not using it correctly. How do we design our enclosures to keep the electromagnetic energy bottled up within and to reject any electromagnetic energy outside of our product? How do we design transient voltage suppression? We've got long cables that are going to be subject to lightning surges. Designing transient voltage suppression to clamp any voltages below the threshold of damage to our circuit is also an important factor. Really, another important factor is where are parasitic components within our circuit? When we design circuit diagrams, schematics, we'll do something like this. We'll have a wire and ground symbols. That's a poor reflection of the complex transmission line structures that we actually put onto our circuit boards. Unless we understand that these parasitic components exist and what their effects are in terms of the impedance on that circuit, we're going to have a bad time. We're going to not have a good design. The danger is that any differential mode inductances can turn into common mode noise as our high frequency current seeks lower impedance paths. The one tool that I would always recommend, says the man who runs a training service for EMC, is EMC knowledge. It's the one thing that you can always take with you. At your next company, you might not have a spectrum analyzer. You might not have the tools that you need. If you know how to design for EMC, you won't have any problems. It's the one tool you can't leave behind. Quick word about the law, and there have been other presentations about this, so I will be brief. Wherever we want to sell our product, in whatever marketplace around the world, there is some kind of EMC regulation. There's usually a regulation. We often have to comply with technical standards that help us demonstrate we're compliant. We have to apply some kind of mark to our product. And there's often a documentation requirement as well. There's also, we need to control production. The sample that we tested, well, if we've made 10,000, is the 10,000th sample the same as the one that we tested? I hope so. If not, how do we perform an assessment between the two? A full reassessment, partial, there are lots of options. Thankfully, due to international technical standardization, that was 3 words that came out very well, there's very similar requirements across the world for electromagnetic compatibility. Similar emissions levels, similar immunity levels. The details may vary, but broadly speaking, they're all the same thing. For instance, in Europe, we either have the EMC directive or the radio equipment directive that ask us to perform EMC tests. This is a legal requirement that we perform an assessment. The process of EMC risk management or EMC specification is also surprisingly in-depth. We have to take a lot of inputs. We have to take the marketplace that we want to sell in, what are the directives, the laws that we have to comply with, standards. We have to consider what its intended use environment is. Oh, the home. Okay, great. What if someone takes a computer designed for the home and puts it in their factory next to a large variable frequency drive system? All of a sudden, it's foreseeable, but not intended use. Do we design our product for that or not? Is there a functional safety aspect? What experience have we had with EMC? And we take all this and we churn it up together, and eventually we come out with a specification for emissions requirements and immunity requirements for our assessment. Usually that assessment takes place in testing. So here's some photos from our EMC test lab, everything from the very, very small to the very big and power hungry. Other requirements are that we might have to gather certain documentation. So in Europe, we have to provide a declaration of conformity with our equipment. This is the legal document where you put yourselves on the hook for the compliance. There's no formal certification in this respect. We have to compile technical documentation that proves we've done enough work to be compliant. There may be certification involved, depending on your environment. Not everything needs certificates. And we need to control our bill of materials with EMC critical components clearly identified on the bill of materials. We need to control production. No, I'm sorry, we can't route the wire this way. It has to go this way, otherwise it's near the noisy thing. Okay, good, you got it. Last bit from me, Unit 3 compliance. What do? We do design reviews. We stop you having EMC problems before you have EMC problems. About a third of our customers pass first time. The other 2/3 have some kind of problem. The third that pass first time, they're either really simple products or ones that we've helped with a design review on. We perform EMC testing. We perform EMC problem solving. One of my best successes, a 50-watt buck boost DC to DC converter. We went from this to this, like almost a times 100 improvement in performance. That was 3 new surface mount components and the rest was circuit board layout. We help you understand the commercial constraints, try and achieve a proportionate, that's our keyword, a proportionate balanced approach to EMC. We provide EMC training. Our next course is in November in Leeds. We give you the tools as well. You need to fix EMC problems. Some of you I know have already picked up one of these. Come and grab one from our stand. We are just over there. Look for the blue and the tall gentleman in the check shirt. EMC doesn't have to be scary. And with a bit of knowledge, you don't have to be scared either. Thank you very much.